Okay, we're starting. So the answers to the quiz are already posted online, but let's actually just run through it very quickly. So this is quiz 3. So something like problem 6 we're going to go over again today, but let's actually look at the others. So true or false, if the product AB is defined and A has a row of zeros, then AB will have a row of zeros. So this is problem 1. AB exists. If A has row of zeros, then AB has row of zeros. So this is an implication. True or false? True. It's actually true. Now let's see who could justify it correctly. So 2, justify. How do you justify?
I say that you multiply a row, and well, there's a lot of factors, but I don't know put into words. There's like m times n, right? And n times m. So m and m.
Okay, so you say, okay, let A be an m by n.
Yes.
And then B be like an n by p or whatever?
Yeah. And,
okay. So these two have to be the same to multiply AB? Sure. What was your argument now?
And m times p will have to be the same size, right? So that means it will have to be equal in terms of like the rows and columns. Because when you multiply A, that's the row, right? And that rows will go into the result as well.
Okay.
And when you multiply the zeros, anything times 0 will have to be 0, and then you add the 0 will always be 0. So once you replace that, it will be that row.
You probably know what you're talking about, but it's hard to say. Yeah. Maybe you could say.
Can you say that the outcome comes from MP? So if you have a row of zeros from A, you will have a row of zeros from for the outcome. And if you have a column of zeros from B, you will have a column of zeros of.
We don't care about columns here, we just care about the rows. So when you want to justify something, again, it comes down to you talking about the definition. How do you define AB?
A resultant matrix with dimensions.
So AB is going to be a matrix C, which is going to be an m by p, right? But how is that matrix defined? Yeah?
C is equal to each entry.
The ijth entry is
equal to the I row of A divided.
It's equal to the ith row of A
dotted with the
dot product
column.
with the jth column of B.
So if you have an I.
So basically, if you have a row of zeros, you're always going to be dot producting a 0 vector with with all the columns of B, and that's going to create a row of zeros. This means assume, and again, I don't know which row of A is going to be zeros. We have to be very general. So I don't know if it's the first row or the second row or the third row or how many rows there are. So assume the ith row of A is the 0 vector. Then the ith row of AB will be, well, it's going to just be the 0 vector multiplied by B1 and the 0 vector multiplied by B2 all the way down to the 0 vector multiplied by BP. And so that would create a row of zeros. So I'm just using the definition. The definition of matrix multiplication is I'm taking the ith row dot product with the jth column. So if you just do that, you get a row of zeros. 4. So how do you define the trace of A? So A I gave you as this vector Aij, which is an n by n, so it's a square matrix. This means that the trace of A, how do you describe it?
That would be A11 plus A22 plus
Mhm.
A33 plus.
It's the sum of the diagonal entries, right? All the way down to A and n. Right? And you could have described that, it's okay to actually also even write it as a summation. So something like that could also work if you want to be more concise, but this is, of course, very acceptable. Yeah.
What was the notation for transpose again? For transposing?
Transpose has a power t. Right, which I think, there, in the bonus I was talking about transpose, so that's there. Okay, so that was your definition. And so now there is a problem in problem 5 that asks you to prove something about trace. So in problem 5, okay, so A is an n by n matrix, B is an n by n matrix, then the trace of A plus B is, what would you guess?
A11 plus B11.
Well, in the first part, just guess a formula for it.
Would it be?
So that would be the correct formula to guess. The trace of the sum of matrices is equal to the sum of the traces of each individual matrix. Okay, and then, so that was part A, to guess a formula. Part B, how did you justify it?
Yeah, sorry. I actually used an example, but A11 plus B11 parentheses plus A22 plus B22 parentheses. So I just grouped them and then put them in parentheses and added.
Okay, so in my proof online, I use this, I think I use the summation notation or something similar, but let's actually just write it out. So we want the diagonal entries of these, so I remember how we define matrix addition, and we're just adding corresponding entries. So the trace of this is actually going to look like A11 plus B11 plus A22 plus B22 plus all the way down to ANN plus BNN. And so that, now this is just a real number. I can just sum all the A's.
What if you use different notations?
B11 plus B22 plus all the way down to ANN plus this is B11 plus all the way down to BNN. And each of these individually is the trace of each individual matrix. There are a multitude of notations you could use. On the solutions that I put online, I actually use different notation than this. But the idea should be the same. The idea is you're summing the diagonal entries of the summation, but you can break that up into just the diagonal entries of the individual matrices. And that, by definition, gives you the trace.
Yeah, I wrote that one. So you just write it like that.
You could write it out like that. You could write it out using summations. You could have written it as, oh, this is the sum of AII plus BII, which by the formula for summations, that's just this guy plus this guy. So that's just the trace of A times trace of B. You could have also said something similar to, oh, this is just the matrix AII plus BII n by n, which is equal to AII n by n plus BII n by n. By definition of matrix addition, and so that's trace. There are tons of ways you could write this down, but the important thing is you didn't give a specific example, and you write something that's general that I can actually match up with a definition. So there are a multitude of ways to write it. I think I used this notation on the solution online because I don't remember how much people remember about series. So I didn't want to be too confusing. Let's actually move on to 6. So 6 is more of what we're going to talk about today. So there's a system of equations. So it's x plus 2y minus z equals 1 x plus z equals 3, 2x minus 4y plus z equals 0. So part A was to state the augmented form of the system. So what did that look like?
1, 2, negative 1, 1, 0, 1, 3, 2, negative 4, 1, 0.
Okay, so that was part A. So now part B says find the reduced row echelon form of this matrix. So you have to put it in a specific form, and of course you're going to use row reduction, right? Which technically it's gauss-jordan elimination, but it's going to be row reduction. So what would you do here?
Add the first two row 1 plus row 2 and
There are a multitude of ways you can continue here, but so let's say I leave this, because I know the first non-zero number in any row should be a 1. So my top left corner is already a 1, so I want that to be a 1, so I'm going to leave that. I also know that in reduced row echelon form, I need everyone here to be a 0.
yes.
So I'll immediately do row operations to get zeros there. So what can I do to get a 0 in row 2? So here I just recopied row 1. What I'm going to do now, row 1 minus row 2 is something that could work. So 1 minus 1 is 0. 2 minus 0 is 2. Minus 1 is minus 2. 1 minus 3 is minus 2. So that creates a 0 here. And I know again I want a 0 here. So what can I do to get a 0? I can probably do something like 2 row 1 minus row 3. So 2 times this is 2 minus that is 0. 2 times this is 4 minus a negative 4 is 8. 2 times this is minus 2 minus 1 is minus 3. 2 times this is 2 minus 0 is 0. So I can have that. And so now I know, so now I've established my first pivot in the first column. So now I'm going to try to attack my pivot in the second column. Okay. So which means I know my pivots in the second should be to the right of anyone above, so I'm going to want to establish a pivot here. Right? So how can I do that? I need the first non-zero number in the row to be 1, so I can just divide that row by 2. So now I've established the second pivot. So there's my pivot in my first column and my pivot in my second column. I immediately want zeros below that. So how would I get a 0 there? Well, I could do something. So here I recopied row 1, didn't do anything. Here I took row 2, I divided by 2. Here to create a 0, what I'm going to do is I'll probably do 4 times row 2 minus row 3. So 4 times this is 8, minus 8, that's 0. 4 times 0 minus 0 is 0. 4 times this is minus 8 plus 3. So that's minus 5. 4 times this is minus 8 plus 0. So that's minus 8.
And now just divide by a negative 5.
Almost. There's something else I want.
Would you divide it by negative 5?
That's right, there's a mistake.
Where?
I don't think that the third row would be the augmented 0.
It's supposed to be
Where?
2 row 1 minus.
Here?
3.
Yeah.
2 row 1 minus row 3.
Yeah, but you're subtracting, so there's a 1. Minus.
It's 2 times 1 minus 0 is 2.
I'm not. Here.
Yes.
Oh, yes. So it's 2 times this minus that. So that's supposed to be a 2. And then to get here, so I would do 4 times this, right, which is minus 8 minus that. So that's minus 10. That's a lot nicer. Okay, so what's the next step here?
Divide by negative 5 to the first row.
I divide by -5. So that's 1, 2, -1, 1. That's my row 1. Here I have 0, 1, -1, -1. That's my row 2. I have 0, 0, 1, 2. And that's my row 3 divided by -5. Okay? So now I've established all 3 pivots. So I'm currently in row echelon form. But the question asks me to bring it to reducer echelon form, so what needs to happen?
2 and first.
I need to kill this guy, kill that guy, kill that guy. So let's worry about one at a time. Let's start by killing that 2. How are we going to kill that 2?
Multiplying the second row by 2.
Take row 1 and -2 times the second row.
Yeah.
So I take this -2 times that, that's 1. This -2 times that, that's 0. This -2 times that, give me 1. This -2 times that would give me 3, right? And to kill this guy, what can I do? I can just add row 2 and 3. So this plus this is 0, this plus this is 1, this plus that is 0, and this plus that is 1. And then I would have 0, 0, 1, 2. And so I still now need to kill this guy. So I can do that just by taking the first row minus the second row. So what I'm going to do now is take row 1 minus row 2. This minus this is 1, this minus that is 0, this minus that is 0, this minus that is 1, 0, 1, 0, 1, 0, 0, 1, 2. And so that's the reduced row echelon form. So that's the answer.
So that would be your solution for the next one?
So that was 6 part B. So now part C, actually to find the solution. So my solution is x, y, z equals, well remember this is my x column, so 1x plus 0y plus 0z equals 1. So my x is 1, my y is 1, and my z is 2. So 1, 1, 2 is the solution to this equation. That was 6 part C. Oh, we actually skipped problem 3. Yes.
Isn't row 1 minus row 3 for the last step?
Row 1 minus row 3. Yes. I need it. It's the same. That's what I need. Let's go back and do problem 3 so we can do one of the bonus problems. So problem 3 said, would the answer to problem 1 change if B had a row of zeros?
Yes.
Yes.
And the answer is yes. And so now we're in the bonus problem. Bonus, justify your answer to 3.
So with that part of it,
You can just pick an example.
You can just pick an example. Right, so if you're disproving a general theorem, you can do it by a counterexample. So I'll just give a counterexample. And it's actually not hard to actually come up with one here. So if I set A, for example, to be 1, 1, 1, 1, and B to be 0, 0, 1, 1, then my AB would be what? This times that, which is 1, this times that, which is 1, this times that, which is 1, this times that, which is 1. So this has no row of zeros. And there are multitudes of examples you can use here. There's an infinite number of examples, but I would just use a 2 by 2. What about the other one? That the other bonus talks about a transpose, I think.
Professor?
Yes.
What if A sub 1, 2 is 0? Then that the row becomes 0 as well?
No, it's this row dot product with that column.
Yeah,
So
so-
it's 1 times 0 plus 1 times 1.
But if the 1 becomes 0 and 1 sub 1, 2, what if that becomes like the whole entire row becomes 0?
If what's 0?
Set A
Which dot product?
1 sub 1, 2. IJ.
Okay,
Yeah,
1,
that-
2.
Yeah.
Yeah?
If that becomes 0, wouldn't that row become 0 as well?
Yes.
So the whole row becomes 0, right? Like wouldn't that become an exception?
Yes, but that wouldn't be justifying your answer. You want to show that if B has a row of zeros, then it's possible for AB to
Yeah.
not have a row of zeros. So if you choose an example that says this has a row of zeros, you didn't prove it.
Well, I was thinking like
You're
something
proving
else.
the opposite. Right, you made a claim that it's possible for you to not get a row of zeros, and now I showed you an example where it's possible.
Because I was
to not
thinking
get
of that, and I was like, you know what?
Yeah.
Just change it.
What about bonus problem 2?
Transpose?
So that one, I defined the transpose for you. So if A, I redefined it in an equation so it can be, you can give me the answer more concisely. So if A is equal to Aij, and it's an n by m, then A transpose can be defined as just me switching the rows and columns. So this is Ji, m by n. Okay? And then I said, if my B is also an n by m matrix, so my B can be written as this, show or prove that this is true. If I take the sum of matrices and I take the transpose, then it's actually equal to the sum of the transpose.
I just put the definition.
I would just do the definition.
That's fine.
So here,
We
so
switched
the
the
proof
rows to
is
column.
A plus B transpose. I can think of this as this matrix. It's just me adding Aij plus Bij for each entry, and then transposing that, which the definition says that just becomes Aj plus Bji. But by matrix addition, that's just Aj plus Bji. And that's just the transpose of each individual matrix. So again, this kind of goes back to show you, as you can see, if you need to prove something, it has a certain property, you really have to follow a definition. You really want to get away from making, well, besides the fact that it's completely wrong, you really want to get away from making general arguments by using specific examples. Because eventually, especially for those of you who are math majors, you'll eventually start working in scenarios where you can't actually visualize what's going on. You won't be able to say, oh, I'm taking this thing over here and this thing over here, because you're working in like 23 dimensions. You can't imagine what these objects look like. It's not going to make sense for you to draw a picture, or it's kind of like this. You're guiding, it's like you're in the dark and you need to feel something out and identify something by some properties that you cannot visualize. You can't give me, oh, it's sort of like this. You have to know things based on the mathematical definitions and prove that they fit into a mathematical definition. Yeah. So we're going to move on. So the answers to this, it's already online. We're going to do more row reduction.
On
I don't think we'll have
Professor,
much time
on
for
the
it.
Juniper website?
Yes. On what?
The Juniper website?
No, the
Juniper ad?
CCNY website.
Oh, the CC, okay.
Where the syllabus is and all that other stuff. So last time we learned about reduce row echelon form and reduce row echelon form. We gave you some examples where you had to identify them. So now we're going to solve some systems by putting them into that form, much like the example here. But what I really want to do now is emphasize to you the kind of answers that you can get and how you can identify when you would get certain examples based on these forms. So we're still in 1.2, and hopefully, I don't know, I kind of want to explain in detail kind of the logic behind the process you're going to do, and so I don't know if you can get through all these examples. Because there are 3 different situations, so I'm going to give you 3 different examples, but I kind of want to explain, so let's see where we get. Use row reduction to solve the following. So I'm going to give you 3 examples. So here's example 1. Minus 2x1 plus x2 minus x3 equals 4. x1 plus 2x2 plus 3x3 equals 13. 3x1 plus x3 equals minus 1. Anyway, row reduction is useful for many things besides solving systems of equations, so it's something that we should get pretty good at doing anyway, so the extra practice will not hurt. So we're going to use row reduction, so now let's kind of go through the process. What would be the first step?
Switch 2 and 1. Augmented mode?
Augment it first, right? You rewrite it, so augment the system. Okay, so we're now looking at this guy. So from now we're going to do with that. And step 2, reduce to REF or RREF. It's really optional unless I specifically require you to do one or the other. So let's actually do that. Minus 2, 1, minus 1, 4, 1, 2, 3, 13, 3, 0, 1, 1. Now, as I mentioned last time, there is no unique row echelon form for a given matrix. There is a unique reduced row echelon form, but by getting to either one, there's a multitude of different techniques that you can use, a multitude of different row operations in different orders that can get you to this answer. So that kind of stands to reason that some ways would be better than others. Like some people will do this and they'll take 10 steps to do it, while another person might take 3 steps to do it. There are some things that are just more efficient than others, so that's kind of what I want to discuss. So the strategy for kind of knowing the most efficient way that I've found is so the first thing you want to do is establish your pivots early. Starting with the top, right? So I kind of know where my top pivot is. It's going to be in this position here. Do this in the easiest way possible. And of course, yes.
It's just the last one is -1 on the solution
Yes.
side.
I'm really out of it today. In my last class, I was doing an example where I was teaching them Green's theorem, and I had like 2 examples that I wanted to give, and I write down the first part of one example and the second part of the other example. It worked out anyway, but it ended up being a lot more complicated than I wanted it to be. But okay, all right. So you want to establish your pivots early, so you kind of know that they're kind of with a full set of numbers. You kind of know they're going to end up in this position. So you kind of want to get that guy first, get that guy second, get that guy third. And I find that in practice, this is going to be the quickest way to actually do it. And do it in the easiest way possible. So there is a multitude of ways to get that 1 in that top corner. Pick the easiest way, right? One possible way is you could just add these 2 rows. But there's an easier way. What's the easiest way to get a 1 there?
That's my -1.
Just add one. Add.
Okay, why wouldn't we divide by negative 2?
Because of the fraction.
It's fraction. I divide by negative 2, it's going to give me fractions here, and I don't want to go through like a whole process with like adding a bunch of fractions. Yeah?
Add row
Then you just
2.
add, yeah. Add row 1 to row 3.
There's an easier way.
Switch.
Switch the rows. Remember, there are 3 lawful things we can do. We can switch rows, we can multiply a row by a non-zero constant, and we can change one row by adding to it a multiple of another row. The easiest, there's already a 1 here. The easiest way to get a 1 there is to just switch these 2 rows. So that's what I'm going to do. So I know I want a 1 here, so what I'm going to do is I'm going to switch the rows to get that 1. So I'm just going to move row 2 up to row 1. And then I've established the first pivot in pretty easy. I didn't actually do any mathematical operations to do this. But once I do that, I immediately want to get zeros here. Don't waste any time, right? So now I'm going to try to do row operations to get zeros there in the easiest way possible. I can't get zeros by switching anyone around, so now I'm going to have to do some row operations. So what can I do here? I can do something like 2 row 2 plus row 1, right? If I take 2 times this and add to that, that will give me a 0. So 2 times this added to that, it's going to give me a 0. 2 times this is 4 added to that, that will give me a 5.
Oh wait, Professor, isn't that row 2 already?
The labels here refer to the previous matrix. So when I say row 2, I'm talking about row 2 from here. So I'm taking 2 times this row and adding it to that row. 2 times 2 is 4, plus 1 is 5. 3 times 2 is 6, minus 1 is 5. 2 times 13 is 26, plus 4 is 30. So I've created a 0 here. I also want a 0 here. So what I can do is something like 3 row 2 minus row 3. So 3 times this minus that is 0. 3 times this minus that is 6. 3 times this minus that is 8. 3 times this is 39 minus a minus 1 is 40. So now I've established my pivot in the first column. Let's go after our pivot in the second column. I need that guy to be a 1. What's the easiest way to get that guy to be a 1?
That's when you can divide by 5.
Here I can divide through by 5 because there are not going to be any fractions that result. So I'm just going to kind of leave these guys here. I'm going to divide through by 5. This is 0, 1, 1, 6. This is row 2 divided by 5. So row 2 from the previous matrix divided by 5. Row 1 I'm not going to really do anything. And I'm immediately going to want to get a 0 here. What's going to be the easiest way to get a 0 there?
Multiply row 2 by 3 and subtract this by row 1.
But then
Minus row 2.
Oh yeah, row 2.
No, it's not go switch. By 3 and row 2 minus 1.
and then row 2 will be times 6.
What?
Just take the row 1 and then multiply it by negative 3.
Take row 1 times negative 3 and
Yeah.
add it.
Why?
Yeah.
But then you have
What would happen?
Anything with the x's.
Yes. The 1 will the 1.
Oh
Yeah, be careful, because in this guy, there's a 1 here. So if I do anything here and add it to that, I'm going to kill the 0. I'm going to lose my pivot. So I don't want to do that. So I really want to use these 2 rows to create that third, that 0. Because then in the first column, it'll maintain the 0. So I really want to look at these 2 rows. Okay?
Okay, then multiply the third one by 5 and the second by 6, negative 6.
But are we getting rid of 6?
Can you just use the
Yeah.
new row 2? That one's.
I can use this row, right? So let's say I can multiply this by 6 and subtract that, or vice versa, right? So now I'm actually using this guy because I've already sort of reduced him. So now it's easy to just multiply this by 6, subtract that, or vice versa.
Why can't we just divide rows, row 3 by 6, like divided by 6?
Because I get a fraction here. It's also possible that you might think of dividing this through by 2 to get smaller numbers, but that's just going to give you an extra step. I'm just going to use this and just do it right away. We really want to be as efficient as possible. So if I multiply this new guy by 6, So here's my row 2 over 5. I'm going to multiply that by 6, and then I'm going to subtract row 2 from the previous guy. So 6 times this minus that, 0. 6 times this minus that, row 3, is 0. 6 times this minus that is minus 2. 6 times this is 36, minus that is minus 4. And so now I can just divide this through by minus 2. So that's 1, 2, 3, 13, 0, 1, 1, 6, 0, 0, 1, 2. So I just took row 3 divided by minus 2. And now all my pivots are established, and I'm in row echelon form. Now, the goal here is what? The goal is to actually solve this system, right? So technically I don't have to go to reducer echelon form, I can actually stop here. So we only need REF to solve the system. There are other reasons why I might want to go further, but not to solve the system. So here is where I'd stop. And so that brings us to step 3. From the bottom row up, rewrite as equations and back substitute. So the bottom row up says I start with row 3. Now row 3 I'm now going to think as an equation. What's that going to give me? That's going to tell me that my x3 is actually 2, right? So this is my x1 column, my x2 column, my x3 column. The last row tells me x3 is equal to 2. So this would mean that if I plug that into row 2, I'm going to have x2 plus 2 equals 6, right? So that's going to immediately now give me that x2 is equal to 4. So now then I'm going to go to row 1. And this is why you really want to start from the bottom row going up, because you're finding all the guys in each successive step that you'll need to plug into a higher equation. So row 2 says I have x1 plus 2 times x2, which I know is 4, plus 3 times x3, which I know is 2, and that should be equal to 13. So this means that my x1 is going to be equal to 13 minus 8 minus 6, which is negative 1. So that's my x1.
So why did we erase one column?
Huh?
Why did we reduce one column though? We
What
had
do you-
4 columns, right? Over there, then we went to 3 columns.
Coming in?
No, from 4 columns, you went to 3 columns?
Well, no, there's the,
Oh yeah, you're right.
Yeah.
Never mind.
okay? So this means my solution is going to be x1, x2, x3. This is now step 4. Write solution using column vectors. Right, and this is basically for the future, we're going to use the column vectors to give us other information like bases and things like that. So it's nice to write them this way. So in our solution, it's going to be this guy. It's going to be minus 1, 4, 2. So I want you to note here, this has a unique solution. This is actually one possibility when you're faced with a system of equations, you can have a unique solution. Right? right? And these steps, the way we're doing it, it's kind of the way I would suggest that you always do it. It kind of keeps you on track, gives you an algorithm to follow. Because really there's a multitude of ways. Like a lot of the suggestions you guys were telling me when I was starting this, they weren't wrong. It was just, it would be very ugly and very messy to actually work through that. You divide at the wrong time, you end up with fractions, or things might just get very messy. And you don't want to end up in that situation. Because row reduction is going to be very important for us, and you need to be able to do it relatively quickly, because at the end of the day, just doing the row reduction on its own is not the point. You want to use the row reduction to do something else, like solve a system, or find an inverse, or whatever. Let's quickly go to a second example. So here's example 2. So this is, say, x1 minus 2x2 plus 3x3 equals minus 2, minus x1 plus x2 minus 2x3 equals 3, 2x1 minus x2 plus 3x3 equals 1. So we're going to do the same thing. First we're going to augment 1 minus 2, 3 minus 2, minus 1, 1 minus 2, 3, 2 minus 1, 3, 1. Right? And you can put the bar here or not. That's really just a reminder to yourself what you're doing. So I want to establish the highest pivot first, so that's going to be that guy. He's already a 1, so I'm literally not going to do anything. So I'm just going to recopy row 1. I immediately want to get below him a 0. So I immediately want a 0 here. So that's my first pivot. I want zeros all the way down here. The easiest way to get a 0 is to just add these two. So I'm going to take row 1 plus row 2. This plus this, 0. This plus this, minus 1. This plus this, 1. This plus this, 1. I'm immediately also going to want to get a 0 here, so I'm going to think of the easiest way to get that. I'd probably do row 2 row 2 plus row 3. So this minus 2 plus 2 times that is 0. This plus 2 times that is 1. This plus 2 times that is minus 1. This plus 2 times that is 7. So now I want to get a pivot here. That's going to be easy. I'm just going to multiply by minus 1. So that's 1 minus 2, 3 minus 2, 0, 1 minus 1 minus 1.
Could you also just switch the rows?
I could also switch the rows, but you could also switch the rows, but that seems easy to me as well. Okay. And yes.
We're allowed to use row 2 even though we changed it.
Huh?
We're allowed to use row 2 even though we changed it.
Yes.
Okay.
And so now, how would I get a 0 here?
Just add row.
I can just add row 2 from the previous matrix plus row 3. What would I get here? This plus this, 0. This plus this, 0. This plus this, 0. This plus this, 8. Right? Now notice this is in row echelon form. Right? So this is already in row echelon form, so to solve the system I don't really need to do anything. So now we just start from row 3. Now what does row 3 tell us? Huh?
Well, I have a problem with it.
You have a problem with it? What?
Yeah, because how do you have 3x1 plus x2 plus x3 equals 8? 0, like you just have 8 equals 8. That's your.
That's
There's
true,
no,
that's true.
there's no value for
Yeah,
x
there's no
three.
value.
I know.
There's
There's no.
How can you get like anything times 0 with
Yeah, so what is this?
It's a constant.
That basically says 0 equals 8, right?
It looks
Absurd.
It's 0 times 0 times a variable.
Basically what just happened is there's no solution. If this system had a solution, it would mean 0 is equal to 8. So we have just found a system that has no solution. It's impossible to have a solution. For you to suggest that this has a solution is the same as you suggesting that 0 is equal to 8.
Even though it could be 0x1 plus 0x2 plus 0x3 plus 8 equals 8.
But that's not what we have.
Well, but the 8.
The
is
equal
constant.
sign happens here.
Okay, there's no hidden constant ever.
There's no hidden constant ever. And we'll realize that is also true when we go back over linear transformations. Remember, these guys represent linear transformations. So they'll only ever represent planes through the origin. There will never be a hidden constant. So this is actually a second situation you can find yourself in. You can have no solution. And usually what that happens in that case is you will always have a form like this in the row echelon form or the reduced row echelon form. You have a bunch of zeros and then something that's not zero, which will never make any sense.
What if everything is 0?
If everything is zero, that is fine. And that's the more interesting case, actually. That's going to be the next example. Let's see. I don't know if we're going to get through that. But it's the same coefficient matrix, actually, my next example. So we kind of know what we want to do. But my numbers over here are going to be different. So if we don't finish this, you guys can actually finish it up at home. x1 minus 2x2 plus 3x3 equals minus 2 minus x1 plus x2 minus 2x3 equals 3. And then I have 2x1 minus x2 plus 3x3. Now instead of 1, I put minus 7. So here we'd have 1 minus 2, 3 minus 2, minus 1, 1 minus 2, 3, 2 minus 1, 3 minus 7. So I want to establish that guy, so I'm going to leave it alone. For this guy, I'm going to add these two. 0, minus 1, 1, 1. This is row 2 plus row 3. For this, I can take this plus 2 times that. 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 And so that's just 2 row 2 plus row 3. And so now I want to get that guy. So this is 1 minus 2, 3 minus 2. 0, 1 minus 1 minus 1. So that's just row 2 divided by minus 1 or multiplied by minus 1. For this one, I'm just going to add these two. Add row 2 plus row 3. And this would just be 0 plus 0, 0, 0, 0, 0. Now this gives me a row of zeros. So now if I kind of go through the process of starting at the bottom row and working my way up, what would that actually look like?
0 and something.
So if I now look at row 3, what is it telling me? It tells me 0 equals 0, which is not wrong. It just doesn't give me any information. Yes?
But you can eliminate, you can get it to reduced form still.
Sure, but for solving the system, we don't actually need that. Now, notice I do not, from these rows, I do not have an equation that has x3 as the lead, right? So what I'm going to do here is instead, just say x3 can literally be anything, because 0 equals 0 is always a true statement. So my x3 has no restriction on what it could be. So I set x3 to be a parameter. And so now let's go into R2. And what does that tell me? This tells me that x2 plus, well, minus t is equal to minus 1. In which case now my x2 is going to be t minus 1. Right? This is always true. My x3 has no restrictions. It can be literally anything. Back substituting into row 2 gives me this equation. Back substituting into row 1 would tell me that x1 minus 2 times x2, which I now know is t minus 1, plus 3 times x3, which I know is t, is equal to minus 2. And so my x1 is going to be equal to minus 2 minus 3t. This would be a minus 2t, so it would be plus 2t. This would be a plus 2, so it will be minus 2. And so that would give me my x1 is actually going to be minus t minus 4. And so now I can write my solution as the following. x1, x2, x3 is equal to, my x1 is minus t minus 4. My x2 is actually t minus 1. My x3 is actually just t.
So that's just many solutions.
Now, for reasons that we'll see later, it is convenient for us to split this up. Let's split it up into two vectors. One where the t is the factor, and another one that is just the constant. So I'll put all the coefficients of t's in the first one. It's minus 1, 1, and 1. Then I'll put all the constants in the other one. So that will give me minus 4, minus 1, and 0. And this would be my solution. Now what I want you to recognize from that is that my t can be anything. So how many solutions do I have here? I have an infinite number of solutions. Literally, I can plug in t as anything, and that will solve my system. It turns out that these are the only three possible cases when you're solving a linear system. You will either have one specific solution. There will only be one coordinate that solves the system. Or there will be no coordinate that solves the system. You'll have no solutions. Or there will be an infinite number of coordinates that solve the system. We'll discuss that in a theorem next class, and we will continue, but we'll stop there for now. Yes, we'll have a quiz. Well, it's just beyond solving systems for now. By the way, an announcement. I think I want to start determinants next, even though on the syllabus I don't think determinants are next. So if you want a shot at the bonus problem for the quiz next week, I'll look after this. I'd look up determinants.
Our determinants will be
Yeah, just look up determinants, and I'll probably also do Kramer's rule pretty soon after that, so you can look up those two for the bonus.